In this section, we are going to talk about adding shortcut connections. So far, our goal is still to implement this final GPT architecture. We started off with this GPT backbone, this dummy GPT placeholder code, and then we filled in individual building blocks. For example, in the beginning, the layer normalization, and then in the previous section, we talked about the GELU nonlinear activation function, and we implemented this small, feed-forward neural network module that we are going to use in the transformer block. However, before we get to this transformer block here, there's one more thing we want to implement, and that is the shortcut connections here. So shortcut connections, they go back to a paper called Deep Residual Learning for Image Recognition. And here the authors implemented a convolutional neural network back then. And they proposed these shortcut connections, or sometimes also called residual connections. So to show you what those are, here's maybe a nice figure. So what they do is, so just to orient ourselves here, what we are looking at is like this, something similar to what we have just coded in the previous section, this little neural network module where you have a weight layer, essentially the NN linear layer, a nonlinear activation function, ReLU or GELU, and then another linear layer. And so this is actually similar to what we're looking at here. Now, what they added is this arrow here. So what they have is they have f of x, where you can think of this here as f of x. So f of x is really this part. It's a function where the input goes through a linear layer, a nonlinear activation, and a linear layer. So you can think of it as a function. And then you add back the input. So input is x, the original input, you add it back to the result of this one here. And so why is this being done? What's the point here? So if you have a very deep neural network, you can have problems like exploding gradients or vanishing gradients. And so, for example, if this doesn't learn anything useful, or let's say it goes to 0 due to the vanishing gradient problem, the network can still use this shortcut. So the shortcut, it doesn't diminish anything. It's essentially like rescuing the network if this is not, you're learning anything useful. So in that sense, you maintain the gradient signal. You maintain a signal during the training to help the network learn something. Otherwise, if you have a very deep neural network, there might be no signal anymore. And then, you have a vanishing gradient problem or other problems. And then the network will fail if one of these submodules fails. Because in a neural network, everything is sequential. These layers are sequential and they depend on each other. And so if one of them does something, does nonsense, then all the other ones will suffer, all the other ones that come below here. So here, as a backdoor, you can kind of learn, or the network can rely on this to skip these layers if they are not useful. It's essentially like a little backdoor here. You can think of it like that. Let's see how that works out in code. So I have also a figure here where you can see a deep neural network with many layers, and we are looking at the gradients here. And you can see the gradients are relatively small. So in neural network optimization, we use an algorithm called backpropagation. We will use that in chapter 5. In this book, we're not really going over the fundamentals of deep learning because, this would be another 500-page book. So here we are really laser focused on LLMs. But some of these deep neural network concepts are relevant. So in this deep neural network, so it's also a convention to draw neural networks from bottom to top. So this is why sometimes when you're looking at these diagrams, why is this, flipped around? This is really a convention in deep learning where people, tend to draw these diagrams from the bottom to the top. So when we follow the inputs here from the bottom to the top, the optimization in the backpropagation algorithm, it goes the other way around. So you start with the output. There's a loss function that's not shown here that is usually used, and then you backpropagate. That's why it's called backpropagation. You go backwards, and you can see the gradient signal becomes weaker. So you have a 0.005. 0.0013, and it becomes weaker, and that makes it harder to learn for the network to learn how to update these weight parameters in these linear layers. And here on the right hand side, you see the same architecture, but I added shortcut connections. And you can see here, so by the way, I'm not making these numbers up. We have actually, or I have code. We will look at this in a few moments. But what you can see is when I add these shortcut connections, you can see that we have much larger gradient values. We have here 1.32 and then 0.26, 0.32, 0.2, 0.2. So we have much larger values, and that helps the network to train better because there's more information for updating these weights here. So let's actually take a look at the code, and let me show you that this is not just a concept, that it actually works. So I just copy pasted this here. This is a neural network where we have 1, 2, 3, 4, 5 of these modules, sequential modules, and each module consists of a linear layer and a nonlinear activation function. So what you're looking at here is the same thing that you can see here. So 1, 2, 3, 4, 5. You can see 1, 2, 3, 4, 5. And then the forward method is computed by calling these layers. So we iterate over the layers here. We're calling them, and then optionally we add this shortcut connection. So I'm saying optionally because just for experimentation purposes, I added argument here, use shortcut, that we can set to true or false, whether to use the shortcut or not. So if we are not using the shortcut, it's just like a regular neural network without shortcut. And if we have this shortcut, then it will add these little shortcut connections. And similar to the paper, what will happen is it will add the input back to the output of the module. So that's what you're seeing here. What you're seeing here. And here, that's without shortcut connection. There's one exception here, if x shape equals layer output shape. So this is essentially when we are, it's just one way, a simple way how I implemented this. Once we are here at the end, we won't add a shortcut connection because that wouldn't work here, right? So there's no point adding a shortcut connection to the output. So this is it. And then I also have a utility function, print gradients, where we get the output. We have some target. So the target really is a placeholder here. How deep neural network training works, we usually calculate a loss function, and then we compute the difference between the value that the network outputs and the target in the loss function. So that is like a measure of, let's say, how similar they are. And based on that, we backpropagate. Now, later on in chapter 5, the targets will be the next tokens we want to generate. And the loss function will be a cross-entropy loss. For now, don't worry about these concepts too much. They are just placeholders here. MSE loss is essentially just the squared difference, the mean squared error loss. Just for simplicity, so that we have something to backpropagate. It's just, we need any loss function here. I just want to keep it simple and self-contained. It has nothing to do with tokens now. This will come later in chapter 5. Okay, so here, let's execute that. And then, of course, we need some values. So for the layer sizes, let's do 3, 3, 3, 3, and 1. The 1 here, the output size is 1 because what we want is something that has the same dimension as the target. So what we want is our network to produce a value that is close as possible to the target, and then we optimize it and so forth. Here, we don't really care about the optimization. We just want to compute the gradients. Then let's do some sample input. So the input is input size is 3, so we need a sample input that also has 3 values. Just for example, 1, 0, y, -1. Why have I chosen those? Just randomly, just something that came to mind. You can try out different values. And then let's do a random seed here. So the random seed is so that you get the same results that I get. And then let's first initialize our network here. So this is our example network without shortcut connections. So this is printing the gradients without shortcut connections. And you can see, these are very small values. So the values in the figure are actually based on the code here. So you can see those kind of match. And then we can do the same thing, with shortcut connections. yeah, and you can see now the values are much larger. So with these shortcut connections, we lift up these gradient values. The network later on, it will be more than just lifting up the gradient values here in the beginning. It will also, learn how to optimize these weight matrices. And if there's something that goes wrong during the training, these shortcut connections can always compensate and rescue the network there from totally failing, because one more time, you can see everything is dependent on each other. So if you have something that doesn't really work here, the later layers in the forward pass, they are not affected. And likewise, if we do backpropagation, if something fails here, this layer is not affected. It can learn how to skip here. And that's the whole idea behind shortcut connections.
Get this book at manning.com.